our first speaker to take over.
Cool. Thank you very much.
And please, if I do mispronounce your name, please correct me.
It's okay. You perfectly, you didn't mispronounce. Okay, good. So let me share full screen. Everybody can see and hear me well?
Yes.
Good. So thank you very much. And I'm going to talk about some scale separation diagnostics and introduce to you the symmetric and bounded efficiency and show how I use them for the intercomparison of precipitation reanalysis. So let me just acknowledge my co-authors, Christian Lussana from Norway and Alice Crespi at EURAC in Italy. This is my talk outline. So first I'll introduce briefly the precipitation data sets I am comparing. And then I'm going to talk extensively about the scale separation diagnostics. So I'll introduce you the energy normalized bias, talk about two scale measures on separate scales, and introduce the symmetric and bounded efficiency. And I conclude with some final remarks at the end. Good. Okay. I cannot go page down. Yeah, here we go. So data. I consider 24 hours accumulated precipitation fields. And the results you are going to see are aggregated on 50 cases of intense precipitations. On the image, you can see a case studies of the 29th of August, 2011. On the top left, you have the COSMO-REA-6 high-resolution regional analysis. This is a 6-kilometer resolution precipitation products. The other three panels are products of the ERA 5 reanalysis. So at the top right, you have the control, which is at 31 kilometers resolution. And then I consider the 10-member ensemble. So I have at the bottom left the ensemble mean. And then I have the spread. And you immediately can see that the COSMO-REA-6 has got much more small-scale details, and the precipitation value, intensities are attained are larger. Instead, the control and the ensemble means are much smoother, so I've got less small-scale details. The ensemble spread, you can see, is very large, but the precipitation is co-located with the precipitation of the ensemble means, which means that the position of the precipitation features is well constrained in their reanalysis compared, for example, to a forecast. And the largest differences between members are due to the precipitation values. So I'm going to compare these precipitation fields with some scale separation diagnostics. So the scale separation diagnostics are a class of spatial verification approaches. And these verification approaches actually account for the field coherent spatial structures and the presence of features in precipitation fields, for example. In a nutshell, what the scale separation diagnostics do is to decompose forecast and observation fields into different spatial components. And these spatial components have got different scales. So they use some filters like wavelets or Fourier or discrete cosine transform. And then they perform the verification on the separate scale components individually, so by using like a traditional verification methods. The rationale behind this scale separation diagnostics is that weather phenomena on different scales are driven by different physical processes. So the idea is that if you provide verification that is depends on the scales of the processes, you provide feedback on these different physical processes. So with the scale separation diagnostics, you can assess the scale structure, the bias, the error, and the skill on different scales. And you can analyze the scale dependency of the forecast predictability. So you have always like a no scale to scale transition scales, for example. On the right, I've pulled out an image from Jung and Leotbecker, where this is an example of a scale components. So you see they use here a spherical harmonic filter to decompose the 500 GZ field. And you can see, there are very small details in the smallest scales, and then every component is characterized by a different, by phenomena on different scales, essentially. So what I do, the ERA 5 and Cosmos Area 6 precipitation fields are decomposed into the sum of components on different spatial scales by using a 2D discrete wavelet transform. And I've decided not to show too many wavelets in this talk, but I have an extra material if people are interested. So, this is, think about each wavelet components as essentially a field characterized by a different scale, which I denote with J. Okay, so the first statistics I evaluate on the different scale components is the energy. So the energy is essentially the average of the squared values of the field, and is proportional to the magnitude and the number of features on each scale. So when I compare the energies for my different reanalysis, this informs on the bias on the different scales and on the scale structures. So for example, this is applied to the images I show you below. So the Cosmos Area 6 has got much more energy on smaller scales because it's got much more small scale details compared to the ERA 5 products. And here you can see that all the products have as dominant features precipitation features around 200 to 400 kilometers. One thing that I wanted to share with you is that the wavelet components have zero mean. So essentially the energy is the standard deviation of the field. And the energy of the largest scale, well, the largest scale is the spatial average. So essentially the energy on the largest scale is the square root of the average. Okay, so this is just to simplify life. So then I compare the energies of my products with the normalized bias. So energy normalized bias, this is the classic bias. So I have suppose the Y denotes the forecast, next the observations, I take the difference, but I normalize it by their sum. Why I want to normalize it? Well, because the additive bias would be very small for small energies and very large for large energies. Even if the relative difference, for example, if you assess it with the ratio, could be like very large in case of small bias or small in case of large biases. So the normalizing essentially enables to compare energies that have different magnitude to start with. And one nice things about the energy normalized bias is that it's bounded. It ranges between -1 and 1, and it's symmetric. So if I swap forecast and observations, its absolute value doesn't change. Instead, for example, for the ratio, it changes. And these are two very important properties for defining later the symmetric and bounded efficiency. Okay, beyond the energy bias, I assess the mean squared error and the correlation as measures of error and associations. So here you see that the mean squared error does not separate very well the three products. Instead, the correlation separates the control, which is the red one, from the ensemble mean and ensemble members. One thing that is important to know is that the mean squared error is composed by different components. Essentially, all the continuous statistics that we usually compute in verifications are related. So there is a bias component. The mean squared error is proportional to the variability of the forecast and the observations, and there is a covariance correlation component. So historically, because the mean squared error is proportional to the variability of both forecast and observations, when I compare, when I verify high resolution forecasts, they usually are overly penalized by the mean squared error compared to their smoother counterparts. So to reduce, say, this effect of the variability, skill scores are used, and usually it's the reduction of variance. It's the skill score that uses for a reference forecast the sample climatology. And the sample climatology is the mean squared error for the sample climatology is essentially the variance of the observations. So when I calculate these scores, the reduction of variance, I essentially normalize the mean squared error by the variance of the observation. So I reduce the variance weight. The reduction of variance is also known as the Nash-Sutcliffe efficiency. Now, this reduction of variance, though, still cannot separate well like the mean squared error, cannot separate well the products, because here in the mean squared error, I still have the effects of the forecast variability. So what we propose is to use the skill score against random chance. And random chance for my wavelet components is essentially the sum of the variability of the variance of the forecast and the observation components. So this is like at the bottom I put like quickly a proof. This is the relation of the mean square error with the mean variances and covariance term. But for wavelets have got zero mean, so this term disappears, and if for random chance there is the correlation is zero, so this term disappears. So you can see that here the mean squared error is normalized by both the variance of the observations and the forecast. So here, because the variance of the forecast is factored in, this scale separation skill score is capable of separating the Cosmos Rea 6 from the control and the ensemble members. So essentially, in a sense, because I am normalizing with also the variability of the forecast, I am giving a chance to the products that have got higher resolutions, and this skill score is kind of more suitable for comparing products of different resolutions. So this is, I've already said all this, but I'll leave it here so people can look at that. This is the summary of what I just said later if they look at the presentations again. Measures of overall performances, like the efficiencies. So the Kling-Gupta efficiency was introduced by Gupta in 2009, and is a measure of overall performance and accounts for the correlation, the variability, and the bias. And the KGE can be interpreted as essentially all the term below the root can be interpreted as the distance of our forecast from an ideal point where the correlation is equal to 1, the ratio between the variability is equal to 1, and the ratio between the means is equal to 1.
All right, Barbara, just let you know that's 12 minutes already.
Okay, I'll be quick. So we introduced the symmetric bounded efficiency, which is essentially defined as the KGE, but instead of using the ratio here, I'm using the normalized energy bias, both for the variability and the bias. And just be super quick. So both the SB and the KGE separate well the control from the ensemble members. However, the KGE is unbounded and asymmetric. So here, when I swap X and Y, you see I have very different results. And because of the ratio, this can attain very large negative values. Instead, the symmetric bounded efficiency by definition is symmetric. And the better performance of the control is dominated by the better representation of the variability on the small to medium scales and the better linear dependence or the correlations. On the larger scales, you see there is instead slightly worse because of a very small over forecast of the bias. So these are my summary and conclusions, and I'll stop here. Okay. Thank you.
Okay. We do have a quick about a minute, and then I don't know if there'll be time to anybody enter anything in the chat, but it's not so much a question, but for me as a hydrologist, I'm curious to know, you're looking at different spatial scales, and of course from a hydrology perspective, it would be interesting to know if this could be recast to look at different temporal scales. So instead of looking over a field, looking at a point and considering metrics that consider different temporal scales. So that's something that would seem reasonable, or?
Yes, actually, I didn't think about it before, but I think it can be put into the other dimensions. Yes, for sure.
Thank you, Barbara. That was a very interesting talk. I will share, I think, the next talk. I'm sorry, I'm just suffering from a bit of a cold, so I have like cotton stuck in my brain. The next talk is by Daniel Serrano, and this is looking at investigating precipitation trends in central and southern Ontario.
All right, everyone. I hope you can hear me well and see me well. Thank you for presenting me. And thank you for coming to the talk. I think I need to share my screen. So let me just do that. Here we are. Can everyone see that?
Yes, I can see
Okay,
that.
great. Sounds good. All right, so my name is Daniel Serrano, and thank you for coming to the talk once again. I'm going to be presenting the first part of my master's thesis, investigating precipitation trends in central and southern Ontario, and my supervisor is Dr. Laura Brown. So to begin, climate change is expected to have different effects regionally, as many of us know. Many areas will experience higher air temperatures and rainfall and higher incidence of extreme weather events. These differences in regional climate can be detected by lakes through changing ice cover periods and changing lake ice thicknesses. These shorter ice periods are also important to consider, especially in the mid to high latitudes, where lake abundance is quite high, up to 40% of the total surface area in some regions. And climate change is also expected to have great impacts on ice phenology. Changes in ice regime will also have an impact on local economies by restricting winter recreational activities, and as well will have impacts on biology and chemistry of lake ecosystems due to the shorter ice-on periods. Just to talk a little bit quickly and to highlight a little bit of the importance of the economy in these areas is in Ontario, for example, during the 2018 and 2019 winter season, the snowmobile industry generated about $1.6 billion and has the potential to generate up to $3.3 billion depending on the weather. And in contrast as well, fishing is really popular in many of these lakes, especially in the winter. Winter fishing generated about $70 million of revenue for these regions in total, including the cost of equipment and as well renting a cabin. Now, going back to the science, most of the research that has been conducted on lake ice has been focused on the higher latitudes, such as the Arctic, where in these places, the climate is generally cold, the winters are long, and there's relatively little precipitation. Much of what we know about lake ice growth and decay has come from studies in these regions. However, when we come a bit down south, things are a bit different. We have a milder climate, even in the winter, where we have temperatures that are sometimes relatively close to zero. Because of this, there can exist periods where the temperatures rise above 0 degrees, which can be accompanied by events of precipitation falling in the form of rain or rains mixes with snow. So the results that I will be presenting today are part of my first objective for my master's thesis, which is to investigate midwinter precipitation trends and projections in central and southern Ontario. And then for the second part, I'll be looking at how they affect lake ice through a computer lake ice model, CLIMO. And I'll be seeing how winter rain can have effect on lake ice processes and phenology. But for now, I'll be focusing on the trends. In this study, I split up the study into two different parts, a long-term study and a short-term study. The short-term study focuses on that red point on the map, which is Halliburton Forest and Wildlife Reserve, located about 3 hours north of Toronto, as can be seen. There's the little red dot. And for the short-term study, I did expand the area to the border that you see around it. These are ecoregions, which are geographical zones grouped by Natural Resources Canada due to similar climates and ecologies. And more specifically, they're the Algonquin Lake Nisiping and the Manitoulin Lake Simcoe ecoregions. You may notice that the Manitoulin Lake Simcoe ecoregion, which is the bottom part, doesn't include the main study area of Halliburton, Ontario, but it was included nonetheless because of the importance of lakes in those areas and the location of lakes near to population centers. The blue pins that you see are Environment and Climate Change Canada weather stations that have available data for the years of 1990 to 2019, which are later used in comparison to ERA reanalysis data. But now let's focus just on that first long-term study where we are looking at Halliburton, Ontario, and I got data from primarily Environment Canada, which has two weather stations, Halliburton A and Halliburton 3, that cover a period of that goes back all the way to 1883. Halliburton A and Halliburton 3 are geographically very near to each other. Number 3 just replaced number A. And then I also included some reanalysis data from ERA 20th century, just to fill in some of the data because there are some data gaps between 1900 and 1942. So here are the results of that long-term trend. So what we're looking at is accumulation, our winter rain accumulations for winters since 1900s to 2019. And we see that winter rain has been increasing faster than snow. We see that by the blue curve. By the end of the century is already about the same level as the snow, which is shown in the gray. And as well, we see in the black as well, the total precipitation. In the red, you also see that there are temperature trends, which also have shown to increase over the about 100-year period. We also see that rain has become more significant over time. Here we see a figure showing the proportions of snow to rain throughout the winter. I split it up, the winter itself, into 3 different segments so that are freeze up, thickening, and breakup. These are because there's importance to the time before before lakes actually freeze. It's been shown that the temperature and weather preceding freeze up will indicate when freeze up actually happens. And so we see that throughout the winter, about 50% of the precipitation that has fallen over that 100-year span on average, about 50% of it has fallen in the form of rain. So clearly there's quite a bit of rain that falls. Splitting up that 100-year period into the individual months and looking at the trends by the individual months, we see that, here we are. We see that the biggest changes and increases in rain were found in the early winter period, that is in the months of November, December, as you can see in the blue and orange curves. And on the other hand, spring showed the least amount of increase of only about 1.25 millimeters per decade, and April did not show any significant trends at all. This may indicate a delayed freeze up due to increased temperatures leading to increased amounts of rain. Nevertheless, we see that November and April had the highest quantities of rain, just that ever since about the 1970s, there's been a switch where November now sees greater rain amounts than the month of April. Contrasting the rain results of snow, snow saw a mix of both increasing and decreasing trends. Positive trends were seen in the midwinter months. These are colder months where snow can predominantly fall. And January and February showed the largest trends with about 1.98 and 1.78 centimeters per decade, respectively. And positive trends were also seen in December. However, spring months did not show any significant trends. Oops, I forgot to show you. These are the sun slopes for those trends. So now expanding the spatial region and then shortening the temporal. So now we're looking at the whole, those ecoregions that I showed you earlier, and as well using mostly ERA5 reanalysis data to perform the analysis. The analysis incorporates years from 1990 to 2019, and the variables that I looked at were total precipitation and snowfall, and rain was thereby calculated by the difference of the two. So I have a lot of results for each of the variables and for each of the months, but here I'm just showing 3 of the months that are about more interesting. Like before, this is similar. The little red dots or blue dots, depending on the figure, shows the Environment Canada weather stations that I use as comparison. And some of them are significant, which I will delve into each one individually right now. So November, for the month of November, I should also indicate that what we're looking at here are ER5 monthly averages of snow and rain, respectively, depending on the figure. So in this case, we're looking at monthly averaged rain. And we see that for this figure, we see that there are significant negative trends, which is indicated by the red color, and the red outline shows the negative, the significantly negative areas in the ERA5 data. And so we see that there's significantly negative trends are found in the lower extent of the Manitoulin Lake Simcoe region, which is kind of closer down towards Toronto, and as well in the area near the Quebec and Ontario border. We see that even in this area as well, in the Quebec and Ontario border, there is a Environment Canada weather station, Chalk River, which also shows significantly negative trends. And as well, we We also see that in the areas around Centerville and Trenton, Environment Canada stations also saw negatively significant trends, really close by to where ERA5 also saw those negative significant trends. They don't quite overlap, but they're almost there. And now looking at the November monthly snow. Oops, sorry, got out of hand. How do I go back? Here we go. Yeah, so now looking at the January monthly average snowfall, we see that there weren't as many trends in snow. And this was one of the months where we saw that there was where ERA5 and Environment Canada both saw significant trends, and that was in this month of January. But we see that they don't quite overlap, and ERA5 data shows a significant trends down closer towards central to southern Ontario near Toronto, or in areas of Orangeville and Brampton, and Environment Canada only saw a negative trend up in Chalk River. And then lastly, in February, the monthly average snowfall trends were also quite positive. And it was mostly in those areas as well towards the south. We see that as well in the center, Environment Canada stations, Eudora were positive, and as well down towards the Prince Edward Island region, Trenton also saw positive trends. So overall, in summary, the long-term study, the 120-year study showed that rain made up about 50% of total precipitation. Rain increased mostly in early winter and least in spring, and the midwinter saw the greatest increase in snow. And then for the lighter half, the short-term study from 1990 to 2019, we saw that early winter saw the most widespread and negative rain trends near Lake Ontario and the Ontario-Quebec border. The midwinter season saw large areas of positive snow trends near the Bruce Peninsula and Lake Ontario regions, and spring saw large areas of positive rain trends spanning from Lake Huron through the middle of the Algonquin Lake Nisbing ecoregion down over to the Quebec border. ERA5 trends were not very strong or significant over the main study site of Haliburton, Ontario, which may be because of Haliburton, Ontario being an area of quite unique topography, which sometimes makes it difficult for some climatic variables to be modeled in that region. And as well, increases in snow trends may facilitate more production of snow and white ice. That's why they're important to study. And while increasing rain trends indicates a thawing of snow overlying the lake ice, and may also lead to more snow ice formation by the refreeze of slush, or if enough snow thawing occurs, it may also facilitate clear ice formation. This will be the next step of my thesis, where I'm going to see how all this additional rain here in this lower latitudes and the mid latitudes can affect lake ice through the study of using computer lake ice model, CLIMO, and I'll be incorporating the effects of rain to this model to see how they may change lake ice phenology and lake ice thickness. Thank you so much.
Thank you, Daniel. That was a good time. That was 12 minutes. I'll open the floor to questions. I don't know if anybody's added anything into the chat. I don't see any. Oh, here we go. We have one question in the chat from Rick Danielson, and he asks, can these trends be connected or used as proxies of prior lake ice as well?
I think maybe I'll have to use Spring CLIMO to see how that how lake ice could have been seen in the past, although it's hard because some variables are missing. But maybe the data set itself can be used, but I'm not sure like right now how trends can be used to connect with proxies. I think they can, yeah. But in terms of local forcing, I think they can. It's just we'll have to be careful with the start and the ending dates of the trends, since that can really affect the direction of the trend.
Thanks, Danielle. Are there any other questions? I had a question, or maybe more of a thought.
Mm-hmm.
So obviously it occurs that differential trends in rainfall and snowfall are not just due to trends in precipitation, but trends in temperature as well.
Yeah.
Have you ever thought of, or have you thought of investigating whether there is some particular threshold temperature where you can diagnose where you expect precipitation to start predominantly occurring as rain as opposed to snow?
That is a really interesting idea. There have been a few studies already looking at some correlations with temperatures in Ontario and Manitoba, but for now, I'm just focusing on the rain, and I just want to see, for what the main part of my thesis is just see run rain through the lake ice model. So for now, that I'll keep that as my focus. But if I have time, that's really something super interesting to look at.
I see there are other questions in the chat. So I just have one question of curiosity. I am not familiar with lake ice modeling. So what would increase rainfall? What would you expect that to actually, how would that affect lake ice coverage?
Like you said before, there's a coupling between temperature and the rain within the winter months. So it will affect kind of the mass balance for one. You'll get more mass in terms of rain, but as well the energy through latent heat and sensible heat additions to the lake ice. So what may happen is the rain and the warmer temperatures can melt the overlying snow, and it can also facilitate the production of more lake ice. The type of lake ice will depend on how much snow actually melts and how much rain falls. So if enough falls such that it's over the lake, we get more water instead of kind of like a slush, it might determine maybe differences in snow ice and clear black ice.
Thank you, Danielle. We have a bit of time, so that concludes both our talks. Is there maybe somebody who wanted to ask Barbara a question again? Okay, well, I guess we can wrap it up there. Again, I want to thank everybody for attending. We still have a number of sessions that are ongoing and parallel stream, so I encourage you all to attend. And I believe there's I guess it's a virtual online icebreaker this evening. So maybe I'll see a few of you there. And other than that, thank you for your participation. And I want to thank the speakers again for their wonderful talks and excellent work. And day one, enjoy the rest of the conference. Thank you. So I guess for Ruth, we can probably stop the recording here.